Have you ever been using your computer
Hmm.
and noticed it just sort of pauses? Not like crashing, just a brief moment where it seems like it's thinking, waiting for something, even if you have a super fast processor.
Yeah, that feeling.
Well, that common fleeting delay often points to a fundamental bottleneck in computing. It's something engineers often call the memory wall.
That's right. It's a classic problem.
Okay, let's unpack this a bit. In the basic von Neumann architecture, which is, under pretty much all modern computers, your processor needs this lightning-fast workspace.
Mm-hmm.
That's dynamic random access memory, or DRAM. It's the crucial link, the sort of middleman, between your processor's tiny, even faster cache memory and your much slower long-term storage like your hard drive or SSD.
Exactly. It's the main work area.
The challenge, though, is that processors have gotten so much faster, consistently outpacing how fast memory can deliver the data.
Exponentially faster, yeah.
And this growing gap, this memory wall, means these powerful processors often end up just sitting idle. They're
Yeah.
literally waiting for the data they need to arrive.
Just spinning their wheels, waiting. It's a huge efficiency issue.
So today we're diving deep into the unsung hero that's been constantly battling this exact challenge, the RAM in your computer.
Yeah.
Specifically, its double data rate, or DDR lineage.
DDR, yes.
Get ready for some fascinating insights and maybe a few surprising facts about how this stuff actually evolved.
And what's truly fascinating here is that the entire history of DDR memory is, it's a direct and continuous response to that very fundamental memory wall problem you mentioned.
Right.
It's really a story driven by an incredible mix of, ingenuity, industry-wide collaboration through groups like JDUS, and just a constant battle against the basic laws of physics.
Sounds intense.
Oh, it is. We'll talk about the elegant simplicity of double pumping, how entire power management systems literally moved onto your RAM sticks, and even why the physical shape of your memory modules keeps changing with each new generation.
The notches changing places.
Exactly. We'll trace this whole journey, starting from that pivotal shift from older asynchronous DRAM to synchronous DRAM, or SDRAM, and the birth of DDR itself. Then we'll go right through the generations DDR1, 2, 3, 4, up to today's DDR5, and even look at what's coming next.
Okay.
We'll explore the core architectural breakthroughs, things like prefetch and banks, the crucial electrical innovations like differential clocks and lower voltages, and that relentless engineering drive to balance power, performance, and density, the PPD trilemma.
PPD trilemma, okay.
And you'll also see how memory has kind of branched out, diversified into specialized types like LPDDR for phones, GDDR for graphics cards, and HBM for high-end AI stuff, each one optimized for very different goals.
That sounds like quite a journey. So
Yeah.
let's start right at the beginning of this evolution. Before DDR, memory used an asynchronous interface, right?
That's correct.
My understanding is that meant the memory controller basically had to, cross his fingers and hope, often waiting extra clock cycles just to be safe when accessing the memory. It sounds slow and, frankly, incredibly inefficient.
You've hit the nail on the head. That asynchronous approach was indeed a major bottleneck. It lacked predictability.
Right.
The real game changer was synchronous DRAM, SDRAM, which came along in the late 1990s. The key insight there was synchronizing the memory's external interface with the system's clock.
Okay, so tying it to the system clock.
Exactly. It sounds simple, but it created predictability. It allowed the memory controller to pipeline commands, meaning it could send a new command while the previous one was still executing without waiting for it to finish completely.
Like an assembly line.
Kind of like that, yeah. Or think of it like a train schedule where everything runs precisely on time. This initial generation, which we now call single data rate, or SDR/SDRAM, transferred data once per clock cycle, typically on the rising edge of the clock signal.
Okay, SDR single data rate.
It was a significant step up from asynchronous memory for sure, but it still had limitations in terms of bandwidth.
So if SDR was maybe a one-lane highway for data, the big leap to DDR, double data rate, was instantly making that same highway 2 lanes wide, but without actually building more road. Is that a fair way to think about it?
That's a perfect analogy, absolutely. The breakthrough of DDR1 was this concept called double pumping.
Double pumping, okay.
Instead of just using the rising edge of the clock signal, it transferred data on both the rising and the falling edges.
Ah, clever.
It was ingenious. It effectively doubled the data throughput for a given clock frequency. So, say a memory clock was running at 100 megahertz, DDR could suddenly achieve 200 megatransfers per second, or MTs.
Wow, just like that?
Yeah, and this was was monumental because it decoupled the external data rate from the internal memory core frequency. It let the bandwidth scale up aggressively without the power consumption and electrical noise problems you'd get trying to run the internal core at impossibly high speeds.
That is really clever. So to manage this double pumping, the internal architecture of the DRAM chips themselves, that must have had to evolve too, right? To keep up.
Exactly. You can't just double the speed of the pipe without making sure you can fill it.
Right.
To feed that faster, double-pumped external interface, DDR introduced the formal concept of a prefetch architecture. It started with a 2N prefetch.
2N prefetch. What's the N?
And refers to the width of the internal data path. So 2N means that for every single external access command, the chip actually fetched 2 data words internally from the memory array. This effectively created an internal buffer, like a small staging area, ensuring data was ready to go when the external bus needed it on both clock edges.
Got it. And what about banks and bursts? Those are terms you hear a lot when talking about RAM. I feel like they're pretty key to efficiency.
Absolutely essential. Yeah. Think of a DRAM chip not as just one big monolithic block of memory cells. Internally, it's organized into multiple independent sections called banks.
Okay.
Having multiple banks allows for concurrent operations. The memory controller can start activating a row in one bank while it's transferring data from another bank. It helps hide latency and dramatically increases overall throughput.
Like having multiple tellers open at a bank.
Exactly like that. Perfect analogy again. And DDR memory accesses are burst-oriented.
Burst-oriented.
Yeah, instead of fetching just one single piece of data at a time, a single command kicks off the transfer of a whole sequence, a programmed number of consecutive data locations. That's the burst. This is way more efficient for the kinds of sequential data access that processors often do, compared to fetching individual words one by one. DDR1 typically used burst lengths of 2, 4, or 8 data words per command.
So the internal architecture got smarter, more parallel, but the electrical side, the actual way signals are sent and received between the memory and the controller. That must have needed some serious upgrades too, right?
Yeah.
To handle the higher speeds and the double pumping.
Oh, definitely. This is where the battle against physics really starts to heat up. DDR introduced differential clocking. Instead of one clock signal, it used 2 complementary signals, CK and CK bar, or CK and CK shop. Because these signals are exact opposites, any external noise tends to affect both equally, allowing the receiver to easily filter it out. This gives an incredibly precise timing reference, which is critical at high speeds.
Okay, clear clock signal.
Crucially, we also got the bidirectional data strobe, or DQS. This is a timing signal that travels right alongside the data bits themselves.
Travels with the data.
Exactly. It acts as the timing reference for capturing the data at the receiver end. This largely eliminates problems with timing skew, where the clock and data signals might arrive at slightly different times due to variations in the circuit board traces. DQS was a huge deal for signal integrity.
Wow, okay.
And DDR also marked a significant transition in signaling standards, moving to stub series terminated logic, or SSTL.
SSTL?
Yeah.
Sounds technical.
It is a bit, yeah. But basically, SSTL is a specific way of designing the electrical interface to help manage signal reflections on the memory bus. Reflections become a huge problem at higher frequencies. They distort the signal. SSTL helps minimize those.
Gotcha. Less distortion.
And, very importantly, DDR1 operated at a lower voltage, 2.5 volts compared to the 3.3 volts common for SDR SDRAM. This was the first step in a really consistent, crucial trend across all DDR generations, continuously lowering the voltage to manage power consumption and heat.
Lower voltage, less power, less heat. Makes sense.
And all of this, by the way, the clocks, the strobes, the voltages, the pinouts, it was all meticulously standardized by the JD Solid State Technology Association.
JD, right?
That standardization is absolutely vital. It ensures that any DDR module you buy from any manufacturer will actually work with any compatible motherboard. That interoperability is key.
That standardization by JD is huge, yeah. Making sure everything just works together globally. Okay, so now let's fast forward a bit through the generations. We went from DDR1, then DDR2, 3, 4, and now 5.
Yeah.
It really seems like a constant race for speed and efficiency, but maybe with different strategies each time.
It absolutely is. Each generation definitely built upon the last, but they also had to adapt to new challenges and opportunities. So DDR1, as we said, gave us that foundational double pumping with the 2N prefetch buffer. It ran at 2.5 volts and hit data rates typically between 200 and 400 MTs.
And it beat Rambus Cram, right? That was a competitor.
It famously did, yeah. RGRM was technically quite advanced in some ways, but DDR offered a much better cost-to-performance ratio at the time, and crucially, it had broader industry backing. So DDR became the standard.
So DDR1 established the baseline.
Yeah.
What was the core strategic insight then that led to DDR2? What did they focus on?
DDR2, which came out around 2003, really focused on tackling signal integrity issues to enable even higher speeds. The really clever part was a kind of re-architecting of the clocking. They ran the internal memory core at half the speed of the external I/O bus.
Half speed inside, full speed outside.
Sort of, yeah. This allowed the data bus, the external interface, to reach much higher frequencies up towards 800 MTs eventually, while the internal logic could run at a more manageable, lower power pace.
Okay, interesting trade-off.
To support this faster external bus, they had to double the prefetch buffer again, this time to 4N. So now 4 data words were fetched internally for each external access.
The 4N prefetch. Got it.
DDR2 also saw the introduction of on-die termination, or ODT. Little termination resistors were built right onto the DRAM chip itself.
On the chip. Why?
To further minimize those signal reflections we talked about right at the source, better signal quality, and the operating voltage dropped again, down to 1.8 volts.
1.8 volts. Okay, so DDR2,
Right.
higher external speed via clocking tricks, doubled prefetch, better signal termination, and DDR3. That one felt like a big push for power efficiency, especially for laptops.
It definitely was. DDR3, starting around 2007, continued that scaling trend. The prefetch buffer went up again to 8 of this time.
8 MP. Okay.
Which allowed the external data bus to effectively operate at 4 times the internal memory clock speed. This pushed standard data rates from maybe 800 MTs up towards 1600 MTs, even higher in enthusiast parts.
So faster again?
But yeah, you're right. The major design focus for DDR3 was really on power efficiency. The standard voltage dropped significantly to 1.5 volts.
Like ice.
And perhaps even more importantly, a very popular low-voltage variant, DDR3L, emerged, running at just 1.35 volts.
DDR3L, I remember that.
That saved critical power, especially for laptops, which were booming, and also for the rapidly growing server market, where power costs are a huge factor. DDR3 also introduced some more sophisticated power-saving features like automatic self-refresh, or ASR, which could adjust how often the memory refreshed itself based on temperature, saving power when cool.
So we're seeing not just raw speed increases, but smarter memory getting better at managing power, too. Now, DDR4 seems like it was a particularly significant architectural shift. Less about just cranking clocks, more about structure, especially with the data centers in mind.
It absolutely was a turning point, yeah. By the time DDR4 came along, around 2014, engineers recognized they were getting diminishing returns from simply increasing the prefetch size again. It would make the internal fetches too large and potentially inefficient.
Okay.
So DDR4 wisely stayed at an 8N prefetch, like DDR3. The key innovation, the sort of new lever they pulled for performance, was entirely architectural. The introduction of bank groups.
Bank groups, how did that help?
Remember the independent banks inside a chip? Bank groups basically grouped several banks together. This allowed the memory controller to issue commands to different groups of banks more rapidly, essentially activating different parts of the chip with less delay between commands. This dramatically increased parallelism and efficiency.
More things happening at once.
Exactly. And this was absolutely crucial for the highly multi-threaded workloads you see in modern data centers with CPUs having dozens of cores.
Makes sense.
DDR4 also introduced a whole suite of reliability, availability, and serviceability RAS features. Things like data bus inversion, or DBI, to reduce power consumption and noise on the data lines, cyclic redundancy checks, CRC, for better error detection during data transfers, and command address parity to make sure the commands themselves weren't getting corrupted.
So more robust for servers.
Definitely geared towards that. And of course, the voltage dropped again even further, down to 1.2 volt standard. Data rates scaled up too, typically starting around 2133 MTs and going up to 3200 MTs officially, sometimes higher.
And that brings us to DDR5, which we're seeing in all the latest high-end systems now.
Yeah.
This one really felt like a truly revolutionary step, not just, an evolutionary one. What was the core insight driving DDR5?
You're absolutely right. It really was revolutionary. DDR5, introduced around 2020, represents probably the most significant architectural leap since the original DDR standard itself. The core insight was to pivot away from thinking of the memory module, the DIMM, as having just one single monolithic 64-bit wide memory channel. Instead, DDR5 embraces on-module parallelism. The biggest change is that a single DDR5 DIMM now effectively operates as two independent 32-bit subchannels. Each one even has its own ECC error correction bits if it's an ECC DIMM.
Whoa, wait. So one stick of RAM acts like two smaller sticks.
In a way, yes. From the memory controller's perspective, it sees two narrower but independent channels on that single DIMM. This allows for much higher memory access efficiency because two different requests, maybe one read and one write, or requests to different memory locations, can potentially be serviced concurrently by these two subchannels.
That sounds like a huge boost for multitasking or multi-core CPUs.
It is. It significantly improves channel utilization. To feed these dual channels efficiently, the prefetch was doubled again, now to 16M.
16N.
And the burst length was also doubled, from 8 in DDR4 to 16 in DDR5. And the 16-word burst times the 32-bit width of the subchannel conveniently fetches exactly 64 bytes of data, which perfectly matches the typical cache line size of modern CPUs like Intel and AMD.
Ah, so it fills a whole cache line in one go. Very efficient.
It's extremely efficient transfer, yes.
That's a huge shift right there, breaking down the channel itself. And I also heard something about the power management moving, like onto the DIMM itself. That sounds like a big deal, maybe for signal integrity or something.
It's an absolutely critical change. Another major architectural shift in DDR5 is exactly that. The relocation of power management directly onto the DIMM itself.
Okay.
There's now an integrated circuit, a power management IC or PMIC, right there on the memory module.
Why move it there?
It provides much cleaner, more localized, and tightly regulated power to the DRAM chips themselves. This is essential for hitting the even further reduced 1.1 volt standard operating voltage and enabling the very high data rates starting at 4,800 MTs and officially going up towards maybe 8,800 MTs in the future.
Wow, 1.1 volts.
Yeah, and having the PMIC on the DIMM helps isolate those sensitive DRAM chips from electrical noise that might be present on the motherboard's main power rails. Better power integrity leads to better signal integrity.
Makes sense. Cleaner power, cleaner signals.
DDR5 also standardized on-die ECC error correction within the DRAM chip itself to catch internal bit flips, improving yield and reliability. And it uses something called decision feedback equalization, or DFE.
DFE.
It's basically an active signal processing circuit right at the receiver that digitally compensates for signal distortions caused by the channel, like those losses and reflections we talked about. It essentially cleans up the degraded signal in real time, allowing reliable operation at these extreme speeds.
Amazing.
It even incorporates some hardware-level mitigations against things like row hammer attack.
Row hammer, where accessing one row can flip bits in the next.
Exactly. That electrical interference issue. DDR5 has some built-in defenses against that.
Incredible. It's just amazing how much complex engineering goes into something we just, snap into a motherboard slot. You mentioned the driving forces behind all this evolution. Besides the obvious need to keep up with faster CPUs, what else has really pushed this forward?
Well, yeah, the CPU memory performance gap, that memory wall, is certainly the primary sort of perennial driver. Processors just kept getting faster, measured in clock cycles per instruction, and they'd simply starved for data if memory didn't keep pace. So DDR's entire history is about constantly trying to feed those incredibly data-hungry processors.
That's an engine, yeah.
But beyond that basic need, it's very much application-driven, too. For decades, demanding applications like PC gaming and multimedia editing really push for higher memory bandwidth for things like textures and high-resolution video.
That gamers always want faster RAM.
Always. Then came high-performance computing, HPC, scientific simulations, things like that, dealing with enormous data sets. They demanded not just more speed, but also huge capacity.
Fair.
But really, in the modern era, say the last decade or so, the most significant driver is undeniably the data center, fueled by the explosive growth of cloud computing, big data analytics, and especially artificial intelligence and machine learning.
AI, yeah. That seems to be driving everything now.
It really is. Training large language models, for instance, is exceptionally memory intensive. It requires just unprecedented levels of both bandwidth and capacity. This needs specifically influenced DDR4's design, particularly the bank groups for parallelism and the enhanced reliability features. And it completely dominated the design philosophy of DDR5, with its dual subchannel architecture for efficiency and the on-DIMM power management for stability at scale.
So specialized, really data-intensive applications are now the main ones pushing the envelope. And you also mentioned this power, performance, and density trilemma earlier. What exactly is that balancing act?
Ah, yes, the PPD trilemma. It's the constant, delicate balancing act that memory engineers always face. It's really the core art of memory design.
Okay.
They obviously want maximum performance, higher data rates, lower latency, greater efficiency, more speed. But at the same time, they have to meticulously manage power consumption. This is absolutely critical for battery life in mobile devices, obviously, but it's also a huge operational cost, the electricity bill, and a massive thermal challenge in data centers packed with thousands of servers.
Right? The heat.
Exactly. This constant push for lower power is precisely why we see those consistent voltage reductions across every single DDR generation, from 2.5V in DDR1 down to 1.1V in DDR5.
Makes sense.
And finally, there's density, the need to pack more and more gigabytes of storage capacity into the same physical space, onto the same DIMM or chip package. This is vital for servers, HPC, and even high-end desktops needing lots of RAM.
So power, performance, density.
And these three factors are intrinsically linked, often pulling in opposite directions. Pushing for more performance, higher frequencies, usually generates more heat and consumes more power.
Right.
Lowering the voltage helps with power and heat, definitely, but it makes achieving good signal integrity, getting clean signals, incredibly difficult at high speeds. The signal margins just get smaller.
Harder to tell a 1 from a 0.
Exactly. And increasing density, packing transistors closer together can also introduce reliability challenges, like making things more susceptible to that row hammer issue we mentioned, or making heat removal harder. So every DDR standard represents a really carefully optimized compromise, a specific point chosen within that PPD triangle, tailored for the target applications of its time.
That makes a lot of sense. It's all trade-offs. And speaking of specialized needs, you mentioned the memory family tree has certainly branched out beyond just the standard desktop or server RAM. It's really no longer one type of RAM fits all, is it?
That's absolutely right. As computing itself diversified into phones, tablets, powerful GPUs, AI accelerators, a single monolithic memory architecture just couldn't serve every need efficiently anymore. That PPD trilemma, that balancing act, really forced the development of specialized branches, each prioritizing different aspects.
Okay, like LPDR, low-power DDR.
Exactly. LPDR was born directly from the necessity of maximizing battery life in mobile devices, smartphones, tablets, thin and light laptops. Its design prioritizes power efficiency above absolutely everything else.
More than speed.
Well, it's still fast, but power is the primary constraint. LPDDR standards often advance on a separate, sometimes even faster track than mainstream DDR. They incorporate significantly lower operating voltages, sometimes even below 1.0 volt now, and integrate much more aggressive power saving states, like deep power down modes where the memory consumes almost nothing.
Wow.
But despite that intense focus on power, LPDDR actually achieves very high data rates per pin, often using wider interfaces within the mobile system on a chip package compared to desktop DIMMs.
Okay, so LPDDR for mobile power saving. Then there's GDDR, which is what graphics cards use.
Yeah.
Why is that so fundamentally different from regular DDR? They both have DDR in the name.
They do share lineage, but graphics double data rate, GDR, is really engineered for one very specific, incredibly demanding purpose, feeding the massive parallel processing engines inside graphics processing units, GPUs. GPUs need to constantly move huge, usually quite contiguous blocks of data. Think textures, frame buffers, geometry data. For them, sheer total bandwidth, the overall data throughput, is far more critical than the initial access latency, the time it takes to get the first piece of data.
Bandwidth over latency.
Exactly. So GDDR makes a deliberate trade-off. It often accepts slightly higher latency in exchange for achieving the absolute highest possible bandwidth. It does this primarily through using much wider memory buses connecting the GPU to the memory chips, typically 256-bit, 384-bit, or sometimes even wider, compared to standard DDR's 64-bit bus per channel.
Much wider highway.
Much wider. And GDDR usually operates at higher clock frequencies and sometimes higher voltages than contemporary DDR to push that bandwidth even further. The latest generations like GDDR6X and the upcoming GDDR7 even use advanced signaling techniques like PM4 to transmit more bits per clock cycle, squeezing out even more throughput.
PM4. Okay, so GDDR is all about raw data throughput for graphics. But for the absolute bleeding edge, you mentioned things like AI accelerators. There's an even more exotic kind of memory called HBM. What makes that so unique?
Yes, high bandwidth memory, or HBM. HBM is a truly radical departure from traditional planar memory layouts. Its core innovation is vertical stacking.
Stacking chips on top of each other.
Exactly. Multiple DRAM dies, the actual silicon chips, are stacked vertically, one on top of the other. They're then interconnected by thousands of tiny vertical electrical connections called through-silicon vias, or TSVs, that run right through the silicon stack.
Wow, like tiny elevators for data.
Sort of. This 3D architecture allows for an incredibly wide memory interface. A typical HBM stack has a 124-bit wide interface.
124 bits, compared to 64 for DDR5.
Right. It's 16 times wider than a standard DDR5 channel. An HBM3E stack, which is the latest generation, can deliver over 1 terabyte per second of bandwidth from a single compact stack.
A terabyte a second, that's insane.
It's phenomenal bandwidth. Plus, the HBM stack is placed physically very close to the processor or GPU die, usually on a special silicon base layer called an interposer. This very short distance dramatically reduces both the latency and the power consumption required to move each bit of data compared to driving signals across a motherboard to DIMM slots.
So super high bandwidth, low latency, low power per bit. What's the catch?
The catch is primarily complexity and cost. Manufacturing these 3D stacks with TSVs is significantly more complex and expensive than making standard DRAM chips. And typically, the total memory capacity you can get per HBM stack is lower than what you can achieve with multiple conventional DDR DIMMs. So HBM is really reserved for the most demanding, bandwidth-starved applications where performance justifies the cost, high-end GPUs, AI accelerators, network processors, things like that.
It really sounds like pushing all these memory technologies, whether it's DDR, GDDR, HBM, right to their limits is just this constant battle against the most fundamental laws of physics.
Right.
What are some of those persistent physical barriers engineers are always having to overcome?
It's a continuous fight, truly. As data rates climb higher and higher and operating voltages drop lower and lower, just maintaining a clean, intelligible electrical signal across the memory bus becomes the dominant constraint, the main challenge.
Keeping the signal clean.
Think of it like trying to have a clear conversation, shouting across a very crowded, noisy room. Signal integrity challenges include things like insertion loss. That's basically the signal weakening as it travels down the wires, especially at high frequencies. It's like your voice getting softer the further away you are.
Okay, signal gets weaker.
Then there are reflections. When the signal encounters changes in electrical impedance along its path, like at connectors or VS parts of the signal energy, can actually bounce back towards the source, distorting the original signal, like an echo interfering with your speech.
Reflections, got it.
And then there's crosstalk. Signals traveling on one wire can electromagnetically induce unwanted noise onto adjacent wires, like hearing someone else's conversation bleeding into yours when the wires are too close. All of these effects, loss, reflections, crosstalk, collectively shrink what engineers call the data eye, which is the window in time and voltage where the receiver can reliably distinguish a logic 1 from a logic 0. As speeds go up, that eye gets smaller and harder to hit reliably.
And I imagine having a really stable power supply must be just as crucial when you're dealing with such tiny voltage margins and incredibly fast signal switching, right?
Absolutely non-negotiable. A stable, clean power supply is paramount. The system that delivers power to the memory chips is called the Power Delivery Network, or PDN.
PDN.
Any instability in the voltage supply, even tiny fluctuations or noise, can directly translate into timing variations, or jitter in the signals, which leads to errors. Robust PDN design is critical. It involves using dedicated power and ground planes in the circuit board, placing lots of tiny capacitors near the chips to smooth out voltage ripples, and minimizing electrical resistance in the power paths.
Complex stuff.
And that move to on-DIMM PMICs in DDR5 we discussed That was a major architectural solution precisely to improve the PDN performance right at the memory module, localizing the power regulation and isolating the sensitive DRAM chips from noise coming off the motherboard. And modern standards like DDR5, as I mentioned, even incorporate active countermeasures like that decision feedback equalization, DFE, which uses digital logic to actively compensate for the channel-induced distortions, literally cleaning up the signal in real time after it's been degraded.
Wow, actively fixing the signal. There's also this thing that confuses a lot of people, the latency paradox. Newer memory generations often have higher CA's latency numbers listed in their specs. Right. CL40 versus CL18 or something, which makes it seem like they're slower to respond. But they're actually faster overall. How does that work?
Ah, yes, the CL number confusion. It's a very common misconception. It's important to understand what CAS latency, or CL, actually measures. It's the delay measured in the number of memory clock cycles between when the memory controller tells the DRAM chip it wants a piece of data, issues the column address strobe CAS command, and when the DRAM chip actually starts outputting the first bit of that data.
Okay, cycles of delay.
Right. And while it's true that the CL number measured in cycles often does increase with newer, faster generations, like DDR5 might be CL36 or CL40, while DDR4 was maybe CL16 or CL18, the crucial point is that the duration of each clock cycle has decreased so dramatically with each generation.
The clock is much faster.
Exactly. So if you calculate the absolute latency measured in nanoseconds, which is CL cycles multiplied by the clock cycle time, it has remained remarkably stable across many generations. It typically hovers somewhere in the 10 to 15 nanosecond range for that first word access.
So even though it takes more cycles, the cycles are so much shorter that the actual time in nanoseconds hasn't really changed much, or might even be slightly better.
Precisely. It takes more ticks of a much faster clock. So the initial responsiveness for the very first piece of data is roughly similar. And for the vast majority of modern computing tasks, which involve moving large blocks of data and benefit from parallelism, the enormous increase in bandwidth, the total data throughput provided by newer generations like DDR5, far, far outweighs any minor variations in that absolute first-word latency. Bandwidth is usually king.
That makes perfect sense. Thanks for clearing that up. And of course, heat is always an issue with high-performance components.
Indeed. Higher frequencies, lower operating voltages, which can increase current, and denser chip packaging inevitably generate more heat. Excessive heat is bad for reliability. It can cause thermal throttling, where the memory slows down to protect itself, and in extreme cases, even data errors. So effective thermal management is absolutely critical. That's why you see those metal heat spreaders on most performance RAM sticks, and why good airflow inside the computer case is so important.
Right. Those heat spreaders aren't just for looks.
Definitely not. And finally, there's a very practical but essential physical point. Each new DDR generation is deliberately made physically incompatible with the previous one.
Yeah, the Nogs moves.
Exactly. They change the pin count slightly, or they move the position of that keying notch on the bottom edge of the DIMM. It forces you to use the correct type of memory for your motherboard, yes, and means platform upgrades are needed. But it's actually a crucial safety measure.
Safety? How so?
It prevents users from accidentally installing, say, a DDR5 module, 1.1V, into a DDR4 slot, 1.2V, or vice versa. Using the wrong voltage or signaling standard could cause immediate, irreparable damage to the memory module, the motherboard, or both. So that physical incompatibility is a key safety feature.
That makes a lot of sense. Better safe than sorry with expensive components.
Yeah.
Okay, so looking ahead now towards the horizon, what's next for memory? DDR6 is definitely on the roadmap, but you also mentioned some potentially revolutionary technologies like CXL that could fundamentally change things, especially in servers.
Right. DDR6 is the next logical evolutionary step for mainstream DRAM. GDEC, the standards body, is actively working on it. They expect to finalize the core specification probably around mid-2025, maybe a bit later. Products based on DDR6 will likely start hitting the market in volume perhaps late 2025, or more realistically, into 2026 and beyond.
And what are the targets for DDR6? More speed, I assume?
Oh, yeah. The target is essentially another dramatic doubling or near doubling of data rates compared to DDR5. So where DDR5 tops out officially around maybe 8,800 MTs, DDR6 is projected to start there and potentially reach well over 17,000 MTs per pin, maybe even higher eventually.
Wow, 17,000.
That would translate to over 134 gigabytes per second of theoretical bandwidth from a single standard memory module.
Incredible numbers. What about the architecture? More subchannels?
That seems to be the plan. Architecturally, DDR6 is projected to build directly on DDR5's successful subchannel concept. The expectation is it will move from DDR5's two 32-bit subchannels per DIMM to four independent 16-bit channels per DIMM.
4 channels on one stick.
Four narrower channels, yeah. This further enhances parallelism and memory access efficiency, and breaking the bus down into narrower channels also helps manage the immense signal integrity challenges at those crazy high speeds.
Makes sense. Narrower channels are easier to keep clean electrically.
Exactly. The burst length is also expected to double again, probably to 32, BL32, to maintain efficiency. Module capacities could potentially reach 256 gigabytes per DIMM eventually, and the operating voltage will likely drop even further, probably below 1.1 volts, maybe 1.0 volt, or even slightly lower, continuing that power efficiency trend. But honestly, the engineering hurdles for signal integrity and power delivery at 17 plus GTs will be absolutely immense.
I can only imagine. Now, what is CXL, Compute Express Link? That sounds like it's potentially more than just an evolution, maybe something that could fundamentally change how computers are designed, especially in data centers.
CXL is truly revolutionary, yes. It's poised to completely redefine server architecture in the coming years. You see, the traditional server model tightly couples a fixed amount of DRAM directly to each CPU socket via dedicated memory channels.
Right. CPU has its own RAM.
But this often leads to what we call stranded memory. One server might have tons of memory, but its CPUs are maxed out, while another server might be CPU-bound but desperately needs more memory capacity that it can't access from the first server. It's inefficient.
Yeah, wasted resources.
CXL fundamentally changes this. It creates an open, industry-standard, cache-coherent interconnect that runs over the standard PCIe physical layer, the same slots you plug graphics cards into.
Over PCIe. Yep.
This allows processors, specialized accelerators like GPUs or FPGAs, and crucially, memory devices to communicate directly with each other over a high-bandwidth, low-latency link. They can effectively share a unified memory address space.
So it's not actually replacing DDR memory itself, but it's leveraging it in a completely new, more flexible way.
That's exactly right. CXL works with DDR. One of the key CXL protocols is CXL.mm. This allows memory expansion modules, which contain standard DDR chips like DDR5 today or DDR6 tomorrow, to be attached to a server via a CXL-enabled PCIe slot. This lets you easily scale memory capacity far beyond what the CPU's direct channels support, potentially into many terabytes per server.
Just adding memory cards like graphics cards.
Kind of, yeah. But even more profoundly, CXL versions 2.0 and especially 3.0 introduce switching and fabric capabilities. This enables the creation of large, disaggregated pools of memory resources, potentially shared across multiple servers in a rack or even across racks.
Disaggregated memory pools.
Yeah, think of it like a shared pool of RAM that can be dynamically carved up and allocated to different host processors or accelerators as needed based on workload demands. This dramatically increases memory utilization efficiency, solving that stranded memory problem, and can significantly reduce total cost of ownership in large data centers.
Wow, that sounds incredibly flexible.
It is. It also facilitates new concepts like memory tiering, where you might have faster, more expensive local DDR memory attached directly to the CPU, acting as a hot tier, supplemented by a larger, slightly higher latency CXL attached memory pool using maybe slightly older or cheaper DRAM acting as a warm tier. So, CXL works hand in hand with DDR, but it transforms server architecture from that rigid CPU-centric model we have today to a much more flexible, data-centric, and composable model for the future.
It sounds like we're also maybe seeing the lines blur a bit between what we've traditionally thought of as fast, volatile memory like DRAM and slower, persistent storage like SSDs.
That's definitely a trend, and it ties into the long-standing quest for a sort of universal memory, something that could ideally combine the speed and endurance of DRAM with the non-volatility, the persistence through power loss of flash storage.
The Holy Grail.
Pretty much. While we're still quite far from a true universal memory, technologies have emerged trying to bridge that gap. Intel's Optane technology, based on 3D X-point memory, was a notable example. It offered persistence directly on the DDR memory bus, which was really valuable for things like in-memory databases that needed fast recovery after a power cycle. Although Optane has been discontinued for consumers and servers, the concept remains interesting.
Right.
And there are several next-generation non-volatile memory candidates still in research and development, things like MRAM, magnetor-resistive RAM, ReRAM, resistive RAM, and FERRAM, ferroelectric RAM. These might eventually find niches, perhaps in embedded systems, or maybe as new tiers within the memory and storage hierarchy, sitting somewhere between DRAM and flash, bridging that gap even further.
Fascinating possibilities there. So let's try to wrap this up. What does this all mean for us, users, and for the future of computing? The story of DDR memory is clearly one of relentless, really ingenious innovation. From that initial, almost elegant double pumping concept back in DDR1, through the scaling of prefetch and voltage drops to the big architectural shifts with DDR4's bank groups, and now breaking down the channel itself with DDR5's dual subchannels. It's just been this constant push for more speed and more efficiency.
A constant battle against that memory wall.
And it really feels like the era of just monolithic, one-size-fits-all memory evolution is definitively over.
Yeah.
We've got all these specialized branches now.
That's a great way to put it. And if we connect this to the bigger picture, the emergence of something like Compute Express Link, CXL, really signals a profound shift on the horizon. Yes, CXL works with DDR, it relies on DDR chips, but it's fundamentally transforming how memory is shared, managed, and utilized, especially in data centers, moving from that rigid CPU-centric model we've had for decades to a much more flexible, data-centric, and composable one. And this raises a really important question for all of us, I think. How will this ability to disaggregate and pool memory resources impact everything? From the flexibility and cost of cloud services we use every day, to maybe even the very design of future personal computers. Will we see CXL move beyond the data center eventually?
That's a huge question. And when you think about it, the relentless explosion of data generation, especially with the incredible rise of AI and machine learning, basically ensures that memory innovation in all its forms will remain absolutely at the forefront of computing.
No doubt about it.
That memory wall isn't some single obstacle that we surmounted once with DDR and can now forget about. It's really a constantly shifting frontier that engineers will always be pushing against.
Exactly. Future progress isn't just going to come from making DRAM chips incrementally faster. It will increasingly depend on holistic, system-level solutions. Things that can intelligently manage a complex hierarchy of diverse memory technologies, fast local DDR, maybe some HBM, pooled CXL memory, maybe even persistent memory tiers, all with that ultimate goal: delivering the right data to the right processor or accelerator at exactly the right time with the maximum possible performance and the minimum possible power consumption.
A complex balancing act across the whole system.
Precisely. So maybe a final thought for everyone listening. As you look around at the tech landscape today, with AI exploding, massive data sets, new computing paradigms emerging, what specific new technologies or applications do you think will be the ones to demand the next truly big leap in memory innovation? What's going to force the industry's hand next time?